Hi everyone. This is part 2 of discussion section 10. So part 1, I talked about some logistics for the course around how we're dealing with the coronavirus and how to get your midterms and everything like that. And then also some review of energy balances. So hopefully you already watched that video and now are coming to this video as the second one. If not, I'll have a link to the first video in the description of this one, so you can click there and go there first. So this is the part of the discussion that's new material as opposed to logistics and review, and we're going to be talking about phase diagrams. So before we get into that, just some quick definitions that you'll definitely need to know. First is that partial pressure, which we call P sub I, so the partial pressure of species I in a mixture, is equal to xi, so the fraction of the mixture that is made up of species I times the total pressure. So that is just a definition that you've probably seen before, but I just want to make sure you're comfortable with. And then also the idea of specific quantities. So a specific quantity is that quantity per mole or per kilogram, so per amount of stuff. So volume is in units of maybe meters cubed, but specific volume is volume per kilogram. And if you remember, density is kilograms per volume, so specific volume is the inverse of density. But that's just an example. You could have, a specific heat, whatever, any quantity, but just giving volume as an example. And we denote that as the normal letter with a bar on top of it. It's really convenient. It comes up a lot using ideal gas if you don't want to carry that N around. The ideal gas law just becomes P V bar equals RT. So that can just make life a little bit easier. And it comes up a lot with our PV diagrams. Okay, so getting into actual phase diagrams. Starting first with PT diagrams, these you're probably more familiar with. These we see in chemistry all the time. So we have pressure as our y-axis and temperature as our x-axis. If you've watched any of my videos, you know that I hate, or come to my discussion section, I really hate memorizing anything, so you should be able to logic out, if we give you the shape of a PT diagram, where's the solid, where's the liquid, where's the gas. At high temperatures, so way over here, it makes sense that, or it should make sense, I hope, that you're going to get a gas. At the highest temperatures for any substance, you're going to get a gas, and at the lowest temperatures, so over here, you're going to get a solid, and then the only phase that's left is liquid. So never try to memorize what goes where. You could logic it out with pressure too, is at very high pressure, you should have solid dominate, but that gets a little complicated. So the triple point is located right here. That is the point where all three phases can coexist. So note that that is a point on a PT diagram. And then the critical point is over here. That is where liquid and gas become indistinguishable from each other. So you're at such high temperature and such high pressure that sort of the concept of liquid and gas doesn't really make sense anymore. We typically don't really approach the critical point, but you should be comfortable like finding it on a graph like this. A couple other things to note with PT diagrams is the slope of this solid liquid line right here is usually the case for a typical simple material. So what we have on the left here, it's usually the case that the higher pressure we go, the more we favor solids. So as we go up in pressure, solids become, a larger part of our phase diagram. But for water, you probably know this, that the density of ice is less than the density of water. And so that means that as we increase the pressure, really what we're favoring is the more dense phase, which for water is the liquid phase. And so that's why for water, the slope is the opposite direction. So as we increase our pressure, our more dense phase, which is our liquid, takes up a higher and higher fraction of our phase diagram. And the last thing to note on PT diagrams is that we are often, and for this discussion section, we'll be doing pure component phase diagrams. So that means this is just water or just X or whatever other simple material we have. But we can extend these to mixtures. So if I told you that water is in a mixture with air, so we're doing a sort of humidity problem, for example, those come up a lot, then at the solid liquid interface, instead of the total pressure being whatever you read off of the y-axis here, the partial pressure of water at the point that water will start to condense out of the vapor phase is what you read off the graph here. So if you're in a mixture, you can think of just changing the y-axis from P to P sub I for the component that you're dealing with here. And I think that will come up on your homework this week. Yeah, so just to reiterate that, if I have water in a mixture with air, then at, let's just say that at whatever temperature I'm picking here, the pressure, so when I'm looking at the intersection of the solid and gas phases, let's just say that the y-axis reads 0.1 atmospheres, just as an example. That means that if I had pure water, so there's no air around, then at 1 atmosphere, our vapor phase water will condense into a liquid phase. If I have a water-air mixture, then the total pressure has the pressure of air in it. So that total pressure isn't super relevant to our phase diagram. But what it does tell us is that when our partial pressure of water in our air reaches 0.1, then the water will start condensing out. And we call that the dew point. So I hope that makes sense. Also, when we're looking at, again with water and air, but also any sort of mixture, we often look at units of ppm, so that's parts per million. And you can just think of that as when we have such a small concentration of something that we don't want to say that xi is 0.00006. So we just multiply it by 10 to the 6 and call it parts per million. So 1 part per million means 1 out of a million particles are species X. So you can really easily convert that from ppm, parts per million, to X just by multiplying xi by 10 to the 6. Will get you parts per million. Okay, so that's PT phase diagrams. Again, probably the type of phase diagram you're most familiar with from your previous classes. PV diagrams are less commonly used, but they are very useful in a chemical engineering context, but I think tend to be a little more confusing to folks who are not used to it. So for the 10th time, don't memorize anything. You should be able to think about which of these regions on a PV diagram corresponds to which substance. So we have our y-axis is pressure and our x-axis is volume. We usually use an x-axis of actually specific volume, just so that we're not saying that we need to draw a different PV diagram if we have 100 kilograms of water or if we have 200 kilograms. If we use specific volume, then our phase diagram will apply no matter how much stuff we have. So I'm gonna kind of annotate this to read V bar. Okay, so trying to figure out which region is which. Well, the first thing that should be pretty easy to remember is that the highest volume species that we have is vapor. The vapor phase is much bigger than the solid or the liquid phase. And so the region on the far right with the biggest specific volume should be the vapor phase. And by similar logic, solid should be on the other end. And then the region that connects the solid and the vapor regions should be the solid vapor phase, right? We need to have a region where solid and vapor phases sort of touch. We shouldn't have to pass through a liquid phase to get to the vapor phase. Sublimation is possible. So the region that touches both the solid and the vapor phase is the solid vapor region. Similarly, we know we have to have a solid liquid region somewhere, and the only region left that touches the solid region that's not solid vapor has to be solid liquid. And then that phase we know has to touch the liquid phase. And then the last thing is that the region that connects the liquid phase to the vapor phase must be the liquid vapor region. And then a couple other points of interest. The critical point is the point above which liquid and vapor are indistinguishable, same idea. And so that is sort of all the way up in this shaded region up here. If you remember from lecture, Dr. Siston was drawing isotherms. And so the isotherm that crosses the critical point looks something like this. And so above that isotherm is our critical region. And then the last area of note is what was the triple point on the PT diagram actually becomes a triple line now on our PV diagram. And so you can identify the triple line because it's anywhere that is touching all three regions at once. So in this area, we're touching the solid liquid up here and the solid vapor down here. So we have solid vapor and liquid accounted for. And then in this region, we're touching solid vapor and liquid vapor. So we have all three phases accounted for. Whereas like once we get over here, we only have solid and vapor. So that's no longer the triple line. That whole orange line across there is the triple line. Cool. Okay, so I want to do a couple practice problems of just working with these types of phase diagrams. Actually, first, I want to note that the PT and the PV diagrams are related to each other. You can think of them as two different slices of a 3D figure that describes your species. So this sort of 3D image, I think for some people makes a ton of sense, and sort of once you see this 3D image, then sort of the connection between PT and PV diagrams makes a lot of sense for sort of spatial thinkers. And I think a lot of people are not spatial thinkers and they just like can't wrap their brains around this 3D image, and that is fine. So I'm really just showing this to you. If it does help you, and if it doesn't help you, it doesn't make sense to you, then don't worry about it. But the way that you can sort of see both shapes is if you look at this from the left, so looking at it from this direction, we have, we're looking at pressure versus volume. And we can sort of see the solid liquid lines, the shape like this that we've been looking at when we're looking at it from the left. And so that gets us a PV diagram. When we're looking at it from the right, so we're looking at it this way, then this region, this whole shaded region here, is flat. And we see it from the side and we only see a line. And similarly, we see a line here. So we end up seeing a line like this, a line that's along this region, and a line that's down here separating solid and vapor. And so we end up with that sort of Y shape that we're used to. So again, if looking at this sort of makes it clearer for you, then awesome. If you aren't as much of a spatial thinker and this doesn't make sense, we're never going to ask you to draw a 3D phase diagram. That would be really mean. But it just might help clarify things. Okay, so now the practice problems that I promised. So what we're gonna do is try to find all 5 of these points described here on first a PT diagram and then on a PV diagram. So this might be a good time to pause and think about if you think you can find these. Before you do that, I want to say one thing, which is looking at the axes of this graph. So if you look at the x-axis, the temperature axis, that's a linear axis. So every tick that's evenly spaced increases our temperature by 50 degrees. However, our y-axis, that partial pressure axis, is on a logarithmic scale. So each tick increases us by a factor of 10 as opposed to by some linear amount. And the reason that we do that is that if we didn't, all of these data down here would be so smushed and compressed on top of each other that it would be really hard for us to see anything about solid vapor coexistence. So you'll see a lot of graphs like these going on in your future chemie classes. So if you haven't seen these before, just be aware that that's what's going on. Okay, so we want to find liquid vapor coexistence, the bubble point, the dew point, and some mixtures of phases. So if you want to pause and think about this, you don't have to write anything. This isn't the participation point, but if you want to think about it and think about where you would try to find these, go ahead and pause. Okay, so the first thing we want is all mixtures that contain both H2O vapor and H2O liquid. So I guess before we start that, we should just label this is our solid region, this is our liquid region, and this is our vapor region. And so liquid and vapor can coexist all along this line. So that whole line right there is part A. And then once we get down here, down below the triple point, we have solid and vapor, so we don't have liquid vapor coexistence anymore. Part B is we want to find H2O liquid at its bubble point at 20 atmospheres. So on a PT diagram, there's no real difference between the bubble point and the dew point. We just have one line at which we have liquid vapor coexistence. So all we need to find is liquid vapor coexistence at 20 atmospheres. And so I guess it's a little hard to see for you guys. Can I zoom in? Okay. So on a log axis, the ticks that are separating 10, 20, 30, 40 on linear scale are not evenly spaced. So our 20 is going to be right here. Hopefully that will show up. There we go. Okay, so we just need to, for part B, follow that line across and we hit our coexistence point right here. So that's part B. Okay, the next question is actually really hard. We need to find the H2O vapor at its dew point at 4 meters cubed per kg. But that, there's no volume on these axes. So we could apply the ideal gas assumption. We don't really know how good that assumption is at this volume. We don't know a lot about like what pressure is that volume. The ideal gas assumption is best at low pressures. So the actual easiest way to do this is to do it on a PV diagram and then come back. So I'm going to do that once we flip slides into the PV diagram. Part D is a mixture of 50 moles H2O liquid and 50 moles of vapor at 1 atmosphere. And so again, just like for the bubble and dew points, we don't really need to know how much there is because we don't have that liquid vapor region. It's just a line. So we just find our liquid vapor coexistence at 1 atmosphere, which is right here, and that is part D. And then the last part for the PT diagram is a mixture of solid and vapor at -13. So we're going to go down on our temperature axis, look for -13. It is approximately here. And so our place that we're looking for is right about here. Okay, so we've done everything but part C, and once we are able to look at our PV diagram, we can come back and do part C on this. So our next slide is sort of the answer key to that, and then we can find the same things that we were looking for in on the PT diagram. We can try to find on our PV diagram. Okay, so the first thing we want is all mixtures that contain both H2O vapor and H2O liquid. So that's going to be this whole region, this whole envelope in the liquid vapor coexistence region. So this whole region is part A. And then the next thing we want is H2O liquid at its bubble point at 20 atmospheres. So just like before, we are on a log axis on our y-axis, and 20 atmospheres is right here. And so we're just going to follow that over to our the envelope where our liquid phase hits our liquid vapor region. And so this is part B. One thing to note on this graph is that it's log scale on the y-axis, but it's actually also log scale on the x-axis. So if you zoom in at kind of a random point, you can see that both in this direction and in this direction, our lines are not evenly spaced. So we are what's called a log-log scale over here. Okay, so now part C is H2O vapor at its dew point at 4 meters cubed per kilogram. That is going to be somewhere along this line over here, which is where our vapor phase touches our vapor-liquid coexistence region. So along our x-axis, we're going to find 1, 2, 3, 4 meters cubed per kilogram. And we're going to follow that up. And where we hit our liquid vapor / vapor region line is where point C will be. And then that makes it so that we can go back to our previous PT diagram. So if we look at what our pressure is at that point, this is 0.01. So our pressure at point C is 0.01, 0.02, 0.03, approximately 0.04. Oh, sorry, this was 0.1. So this is 0.4 atmospheres. And so that lets us go back to our PT diagram, and we can just look for 0.4 atmospheres. So this is 0.1 right here, 0.2, 0.3, 0.4 is right about here. So this is something that PV diagrams can help us do, is to connect back to the PT diagrams. Okay, so we've done parts A, B, and C, and now we need parts D and E. So we want a mixture of 50 moles H2O liquid and 50 moles vapor at 1 atmosphere. So we know that any mixture of liquid and vapor at 1 atmosphere are going to be somewhere on this line. So this is our liquid vapor mixture at 1 atmosphere. But we have been given specific amounts. So we're 50% liquid and 50% vapor. And so we're going to make an approximation here, which is that our liquid volume is going to be extremely small compared to our vapor volume. Whenever we have a mixture of a solid and a vapor or a liquid and a vapor, the vapor is going to be almost all of our volume. And so if we know that 50% of our mixture is a vapor, then that means that the volume of our system is going to be about 50% of what the volume of the system would be if it was 100% vapor. So if we look at when our system is at 100% vapor, we can call that, I don't know, 1.8 atmospheres, or sorry, 1.8 meters cubed per kg. And then when we have a 50-50 mixture, our volume is going to be about half of that. So our volume is 0.9, so 1.8. We're going to connect it down here and say that's 1.8. And so our volume, that's our volume when we're entirely gas. And so when we're half gas, we'll have half that volume. And so we'll be at 0.9, which is right here. And so point D is right here. And so you can think of this in two ways. One is that this makes it harder. You know, you have to think about that line, but it also gives you more information. If you know what point you're at in a coexistence region on a PV diagram, then you can figure out what fraction vapor and what fraction liquid you are, whereas a PT diagram doesn't give you any of that information. Okay, and then the last thing is part E. So we have a mixture of 90 moles of H2O solid and 10 moles of H2O vapor at minus 13C. So if you remember, this down here is our solid vapor coexistence region, so we'll be somewhere in there. And then at minus 13 degrees C, we don't really know what that means on a PV diagram. So that's where it becomes useful to connect back to our PT diagram. And at minus 13 degrees C, we were at about 0.002 atmospheres. So if I'm connecting that over here, we're at about 0.002. And so if we go back to our PV diagram, we know that we will be anywhere that we have a solid vapor coexistence at minus 13 degrees C will be along this constant pressure line at 0.002 atmospheres. And so that whole line is our solid vapor coexistence at minus 13. And then we have, again, this information about amounts. And so we can make exactly the same assumption that we made before, that the vapor phase is going to take up almost all of our volume relative to our solid phase. So if we are 10% vapor, which we are here, then our system will have 10% of the volume that it would have had if it was 100% vapor. So if we look at our line, we can say that if we were 100% vapor, we would have about 200, 300, 400, 600 meters cubed per kg as our volume. But if we have only 10% vapor, then we can say that we would be at 10% of that. So that would be 60. So 10, 20, 30, 40, 50, 60 meters cubed per kg. So point E is going to be right here. Okay. So hopefully that makes sense. If you want to sort of pause and go back and think about why these points are what they are, you can go ahead and take a minute to do that if you would like. Okay, so the next slide is just sort of the answers to that in actual type instead of my chicken scratch. So if you want to look at that, you can. Also, as always, I'll be posting these slides if you want like the actual images. Okay, so our next problem for practice, we're going to be taking PT diagrams and converting points that we find on the PT diagram onto a PV diagram. So path 1 is in blue here on the PT diagram, and path 2 is in purple. And what we want to be able to do is draw both of those paths on the PV diagram. And then also finding these specific points, so point A, B, C, and D, and looking for specific volumes at those points, which obviously specific volumes are sort of the whole point of having a PV diagram, is being able to find those specific volumes. Okay, so if you want to finding those, go ahead. I'm going to switch over to my Notability app where it's a little bit easier for me to draw things. Okay, so starting with path one. Path one is a little bit easier to draw just conceptually on a PV diagram than path two is, because pressure is our y-axis on both of these diagrams. And so if we have a line that is at constant pressure on our PT diagram, it's going to have to be at constant pressure on our PV diagram as well. So the pressure that we are at for path one is 20 atmospheres. So just reading off the axis here. So this is, oops, that was very okay. And so we know that our path on our PV diagram is also going to be a straight line at 20 atmospheres. What becomes a little harder is finding these specific volumes and finding if our line ends at a certain temperature, what volume does it end at? So going into our PV diagram, we know that we will be a straight line at 20 atmospheres, which is right here. And we're gonna just draw a straight line sort of somewhere along there. And we don't yet know where we're gonna end. So point A was our, so if we label on our PT diagram our phases, this is solid, liquid, and vapor. And so point A is at our solid liquid coexistence. And so point A is actually going to be this whole region here. It's a pretty small region, but the whole region between it that's in the solid liquid coexistence. Similarly, point B will be where our liquid and vapor coexist. So point B is this entire region here, where we have coexistence of our liquid and our vapor. And then what we want is our liquid specific volume at point A and point B. And so to find our liquid specific volume, we just need to, similar to our logic before where we were finding the volume of mixtures, this is sort of the opposite, is if we are somewhere in a mixture, then our specific volume is partly the specific volume of our liquid and partly the specific volume of, in this case, the solid. So the specific volume of just the liquid phase will be the same as the specific volume if we had a pure liquid. And so our liquid specific volume will be along this line here. And so if we read down, that's about 0.0002. So our answer to the first part of that question, what is the liquid specific volume at point A, is 0.0002. And then point B, we also want the liquid specific volume. So this in here is our liquid vapor coexistence region. And so our pure liquid is over here and our vapor is over here. And so the specific volume of the liquid in our liquid vapor mixture is going to be the same as the specific volume for a pure liquid. So if we read off the specific volume, you know, somewhere in the middle, like here, I'm going to erase that so that you don't think that that's the answer. We would be getting a specific volume of a liquid vapor mixture. So it would be artificially big because we have a bunch of really big vapor in there. Whereas if we look at our pure vapor, or sorry, our pure liquid part of the line, that is where we have pure liquid. And so anywhere in our coexistence region, the specific volume of just the liquid part of that coexistence will be this that we're reading off here. And that is about 0.0003. So then our answer to part B is about 0.0003, roughly. Okay, so now we can transition to the second part, which is path 2. This part is a little bit harder because something that is at constant, I guess one thing that we can do before we and is, before we finish talking about path 1, is where does it end? And so we can see that path 1 ends at 450 degrees C, but what volume will that correspond to? And here's where we sort of have no choice other than to use the ideal gas law. And so, like I mentioned earlier, our ideal gas law is PV equals nRT. Hopefully you guys are comfortable with that. And then if we translate into the specific volumes, that's like saying PV bar equals RT. And so in our PV diagram, we are at constant P for path 1. And so we can do, V1 over V2 equals T1 over T2. And so if we know that our specific volume, when we just got to the vapor phase here, was about 0.03, and we know we can read its temperature off the graph here, and that is about 237, then we can say V1 is about 0.03, and T1 is 237 plus 273. So remember, whenever we're using the ideal gas law, we need to convert to Kelvin. And then V2 is what we want to find, and our T2 is 450 C plus 273. And so that lets us solve that V2 is 0.04. And so this line is going to end at 0.4 meters cubed per kilogram. So this is 0.1234. So it's going to end right here. So that's where path 1 ends. Okay, so sorry for that little diversion. Forgot to talk about that before moving to path 2. So now path 2 is much harder to calculate than to draw on our PV diagram than path 1 was, because an isotherm on a PV diagram is going to look something like this, right? So it's not a nice, easy straight line. If you're confused about the isotherm concept, Dr. Siston talked about it in lecture this morning. And also, if you look at that 3D PVT diagram, you can see the isotherms along there. But we'll sort of step through it here. So one thing we know for sure is that we are starting somewhere in the liquid region up here, and we are ending somewhere in the vapor region. And we are doing so at 150 C. So I'm reading that off of the x-axis here. And we can figure out at what pressure we're going to go through our liquid vapor coexistence by looking at this point here. And so that point is 2 atmospheres. So one thing we know for sure on our PV diagram is that we're going to cross through our liquid vapor coexistence region at 2 atmospheres right here. And we also know what pressure we start our path at. It's at 100 atmospheres. And so we're going to start somewhere up here in our liquid region, get down to this envelope, and then hit our liquid vapor region, go across at constant pressure. So we're at constant pressure, but changing the volume as more and more of our mixture becomes a vapor from the liquid phase that it was in before. And then we're going to go into the vapor region, but that gets a little complicated. So before we go there, I want us to do everything we need to do here. And so the first thing is sort of finding point C on here. So point C is our liquid vapor coexistence. So point C is going to be this whole line right here is point C. And so what we want is, what is the vapor specific volume at C? So very similar logic to what we had before. The vapor specific volume is what is the specific volume of the vapor phase, and that will be the same as if we had pure vapor, what is the specific volume of our total thing. And so we can read that over here off our envelope, and we get 0.2. So the vapor specific volume at 0.3 is 0.2 meters cubed per kilogram. And then we now need to find part D. So one thing we know for sure about part D is that it's going to be at 0.01 atmospheres. So it's going to be, I guess it's a little hard to read with all my scribbles on top. Point D is actually at 0.02. So we know that it's going to be somewhere along this line, but we don't know what volume we're going to be at. And so what we can do is, using the ideal gas law, we can try to find what kind of line will connect this point right here to on an isotherm to down here, and sort of what that slope will be. So again, starting with the ideal gas law, we have PV bar equals RT, so that's why there's no N in there, and we can solve for pressure. So P equals RT over V. In this case, we're at an isotherm, we're at, in this case, 150 C, so RT. In this graph, we're on a log-log axis. So we actually want is a relationship between log P and log V. So if you remember your log rule, I can rewrite this as log P equals negative log V, because it's in the denominator, plus log of RT. And so the relationship between log P and log V is linear, with a slope of -1. So that lets us draw a line with slope 1 that will go from through our vapor phase, starting at our coexistence point. And where that gets us is about here. So that straight line goes like this. Sorry, my lines are not as straight as they probably could be. And so this is point D. And we can read the vapor specific volume to be 20 meters cubed per kilogram. So point D, the answer is 20. Okay, I think that last bit is a little bit complicated, but another thing that we could have done is just that what's good about doing it this way is it gets us our whole line. We can continue this line forever. And so it gets us more information. But if really all we cared about is point D, we could also have just plugged our pressure and our temperature from our PT diagram in and solved for our V, and that would have been fine. Okay, so that is the end of this question. And then the last thing I wanted to go through really quick is, so this is just a prettier drawing of that answer I just gave. The last thing I wanted to talk about was linear interpolation. So this comes up a lot in energy balances because you often have, a heat capacity at one temperature and a heat capacity at another temperature, but you want to know, the heat capacity at some other temperature in between, or enthalpy. So a lot of times you have tables that have values close to what you need, but not quite the one that you're looking for. So I'm showing here, just as an example, if I have some enthalpy of some substance, don't worry about it, exactly what substance this is, just an example. I have the enthalpy at 200 degrees C, and I have the enthalpy at 250, and I want the enthalpy at, say, 220. There are two equivalent different ways of doing this, and I think this is where the age difference of when I went to middle school versus when you all did. I never learned point slope form, if that's something you're really comfortable with, then cool, use point slope form, throw it in there, and then plug in your new value. I am told that this equation is point slope form. I never learned that. That's not something I'm really comfortable with. So the way that I do it, which totally works, and I think involves less memorization, which is always what I hate, is I just remember y equals mx plus b, the sort of go-to formula for a line. And I know that m is my slope, which is rise over run. So that's y2 minus y1 over x2 minus x1. So I guess just to be clear, my x-axis, this would be x1 and y1, and this would be x2 and y2. So I have 2 points, x1, y1, and x2, y2. So my rise over run is just y2 minus y1 over x2 minus x1, and that gets me my slope. And then I just plug one of the points in and solve for b. So for this problem, I would find my slope to be y2 minus y1 over x2 minus x1, and I get a slope of 1.9. And then, oops, I know that my equation is y equals 1.9, my slope, x plus b. I plug in one of my points, so in this case I'm plugging in y1 and x1, and I solve for b. And so then I know that my whole equation is y equals 1.9 x plus b that I just solved for, and I can solve for y being 2900. So this is just a super simple example of how to do linear interpolation. I don't know if it comes up on this homework in particular, but it definitely will come up probably in this class, but certainly in the future. I use linear interpolation probably more often than I should in my research, so it comes up a lot. Okay, so that is all I have for this discussion section. I hope this all made sense. For the participation points, I'm going to put an assignment up that's going to be basically describe what this second PV diagram practice problem was. So again, like I mentioned in the first video, the point of these participation points for discussion section isn't, I'm not going to be grading them for correctness. I'm going to be grading it for, can I tell from what you wrote that you watched this video? So anything along the lines of translate paths from PT diagram to PV diagram. Like, there was a blue line and a purple line. Just write like one sentence that shows me that you heard me talking about this practice problem. No need to demonstrate any sort of knowledge, just that you watched this video. So this is the practice problem I'm referring to on that. That participation assignment is going to be due at the end of the day, Friday. So you have a few days from when I'm posting this. It's currently Tuesday, to get that uploaded onto bCourses. So again, please don't like take half an hour and write a whole paragraph. Write me one sentence that shows that you were here. Okay, I hope this was helpful. Please don't hesitate to come to office hours or email me or use Piazza or whatever else you may need if this was at all confusing. Okay, thank you. Hope you all are staying healthy and safe.